Example 4.4.6. All right, setup for this one is a little bit different. It says you just won the lottery. The jackpot is advertised as 300 million, but you have two choices for how to receive the winnings. The prize may be paid out as an annual annuity of $10 million over 29 years, with the first payment today and the 30th payment 29 years from today, or as a single lump sum payment of $130 million today. If you expect to earn 8% on your investments, which payout option offers the highest present value? Okay, so this is typically how lottery winnings will get paid out. The jackpot will be called a $300 million jackpot, but if you take a single lump sum payout, it'll typically be around half of that amount, sometimes even less. In this case, it's $130 million. The reason they can call it a $30 million jackpot is because one of the options to receive the payments is to receive 30 payments of $10 million over the next 29 years. We could call it the next 30 years, with the payments just happening at the beginning of each year instead of at the end. So the end of year 29 is also the beginning of year 30. So you get 30 total payments of $10 million, which totals $300 million. All right, and so we're faced with this option. We have to pick which one. Obviously, this is an example crafted for interest. It's just kind of fun to think about winning the lottery. It may not seem like a practical example because, which one of us is going to win the lottery? Probably none of us. Maybe one of you will. I'll be praying for you. But we will, all of us, if we live long enough, are probably going to be faced with some sort of payout option like this. And that's because typically retirement payouts will be structured this way. You'll either have a defined benefit plan at your employer, that is where you just pay in a little bit, the employer invests the money on your behalf, and then they promise to make some sort of set payments once you retire, or once you reach retirement age and retire. And you'll have a choice on how to receive that payout. You could receive it as an annuity, so a set payment, probably each month, over X number of years, possibly for life, just depending on how it's structured. Or you could take a lump sum payout up front. You could get the entire amount up front, and then you're in charge of managing that money for the rest of your life. Life insurance payouts will often be structured this way as well. So if you have a life insurance policy on a family member and they unfortunately pass away, you will often have a choice on how to receive that payout. You can either take a lump sum up front, or you'll be able to take an annuity over X number of years. So although, of course, none of us are likely to win the lottery, we will have to make decisions like this at some point, so it's good to know how to deal with these types of decisions. So, to make it more fun and interesting, let's think about winning the lottery. All right, so we have a choice to make. We can either take the lump sum payout of $130 million today, or we can take the annuity of $10 million over the next 29 or 30 years, depending on how we're thinking about the year cutoff marks. So we've got a time value money problem. We have cash flows over different points in time, and we need to evaluate them. We need to figure out which one offers the higher present value, right? If we convert everything to the same units, we take the payout today of $130 million. That's already in today's dollars, so that one's good to go. Or we take the $10 million payout over the next 29 years. If we convert that annuity into today's dollars, then we can directly compare those two payout options. We can compare the annuity with a lump sum and say which one is more valuable based on the interest rate we expect to earn on our investments. So let's use our three-step process where step one is mapping out the cash flows. And in this case, we have two choices. So we can take the lump sum payout, and if we take the lump sum payout, we have just a single payout. So at time period 0, we would receive $130 million. All right, and that's it. We could draw the timeline on out, but there are no other cash flows associated with it. There's just the one cash inflow of $130 million today. So that's the entire timeline for the lump sum payout option. For the annuity option, we've got something a little bit different. So for the annuity, we are looking at a series of payments of $10 million, with the first one actually being received today. And then we'll receive an annuity, a $10 million payout, each year at the beginning of the year. So 1 year from today, we'll get the second payment of $10 million. All right, and that pattern will continue. So we'll do our little broken mark here and do our ellipses, the 3 dots, to say this pattern continues on out to 29 years from today, which is the beginning of year 30, when we receive the 30th, even though this is at the 29th tick mark, it's the 30th $10 million payment because we started at 0. And so if we were to actually map out 30 years on this timeline, we'd have the end of year 30 right here, but there's no cash flow here. So this is blank spot at the end of the timeline at the end of year 30 because the payments are happening at the beginning of each year. Right? We have an interest rate associated with this one that we need to account for since the cash flows are happening over time. That's 8%. Okay, now we need to compare these two. Well, the easiest way to do that is going to be compare the present value of the two cash flows, and that's because the lump sum payout is already in present value terms. It's in today's dollars. And of course, if that even didn't pick up on that, we could compare future values. There's nothing wrong with that. We'll come to the same conclusion, but it'll just save us a little bit of work to compare present values. But even if we didn't pick up on that, in this particular problem, it actually tells us which payout option offers the highest present value. So we know that's what we're looking for on this particular problem. Okay, so that's step 1. We have mapped out all of the cash flows associated with this problem. Step 2 is to identify what type of cash flow we're looking at. We've already said that we've got a lump sum payout with a payout up front, and the problem described the $10 million payout as an annuity, but we have 3 different types of annuities. We have ordinary annuities, we have an annuity due, and then we have growing annuities. Well, we know this particular annuity is not a growing annuity because the cash flows are level. It's $10 million every single time. So we know it's either an ordinary annuity or it's an annuity due. And if we look at our cheat sheet for annuities, we'll look at these descriptions and example timelines and see if we can figure out which one it is. The ordinary annuity, which we've looked at in examples before now, has payments at the end of each period. So we have this blank spot today where nothing happens at time 0. And then the payments start at the end of the first year, and then at the end of the second year, the end of the third year, and the last payment is at the end of our timeline. If we compare that with an annuity due, where an annuity due is described as a finite series of equal cash flows at regular intervals paid at the beginning of each period, we can see the cash flows are bumped up starting at today, at time period 0, because that's the beginning of year 1. And then the second payment is at the beginning of year 2, which is also the same thing as the end of year 1. The third payment is at the beginning of year 3, which is the same thing as the end of year 2. And then we have this blank spot at the end of our timeline because at the end of year 3, there's no payment. This one just happens to be a 3-year annuity. Right? Well, this is what our payout looks like with the lottery option. The first payment of $10 million happens today. Right? It happens right now, so the payout's at the beginning of the year. And then after that, every single year, we receive another payout of $10 million, with the last one 29 years from today, which is actually the beginning of year 30. And at the end of year 30, we have this blank spot. There's no extra payout there. So we are looking at, for the annuity, this guy is an annuity due. All right, we have the exact same tools available to evaluate an annuity due. So once we know that it's an annuity due, we can select our tool and actually evaluate this thing. And it's the same 3 tools that we have for ordinary annuities. We've got the present value, future value of an annuity due formula, the time value money keys in a financial calculator, and of course the spreadsheet. We won't talk about the spreadsheet in this video. We're going to focus on the formula and the financial calculator, since that is most likely what you'll have access to in the exams. And I do want to talk a little bit about this formula before we get too far. Well, I guess we need to select whether we're looking at the present value or future value of an annuity due. In this case, we know we've already discussed that we're looking for the present value. So we're going to use this present value of an annuity due formula. And let's look at these guys real quick. I'm going to compare the present value of an annuity due formula with the present value of an ordinary annuity. So if we look at the present value of an annuity due, we have the payment divided by the interest rate times the quantity, 1 minus 1 over 1 plus r to the n. This section right here is what I want to focus on. All right, we have this extra quantity out here. It's times 1 plus r, but ignore this guy, the 1 plus r, for just a second. And let's scroll up and look at the present value of an ordinary annuity. If we look at the formula for the present value of an ordinary annuity, this ought to look really familiar because we just described it. It's the payment divided by the interest rate times the quantity, 1 minus 1 over 1 plus r raised to the n. This is exactly the same series of terms that appears in the present value of an annuity due. Right here. For an annuity due, we just add an extra 1 plus r. We multiply it by an extra interest rate factor. Now, why is that? If we look at these timelines, we can get a sense of what's going on here. So when we're calculating the present value of an ordinary annuity, our first cash flow happens 1 year from today. So it's going to get discounted using our discount factor, 1 over 1 plus r. This one's going to come back 1 year to get turned into time period $0, right? It's expressed in end of year $1. We'll discount it back. This formula will discount it back for us 1 period to express it in today's dollars. And that's going to happen with every subsequent cash flow. The one at the end of year 2 is going to get discounted back 2 years to be expressed in time period $0. The one at the end of year 3 is going to get discounted back 3 years to be expressed in time period $0. Well, if we look at the timeline for an annuity due, all of these cash flows are bumped up 1 year. In fact, this first cash flow right here is already in today's dollars, and it doesn't need to be discounted at all. We don't need to discount this cash flow because it's already expressed in today's dollars. So we want to leave that one alone, right? Remember, with the ordinary annuity, it was discounted 1 year to come back to time period $0. So this first cash flow has one extra compounding period attached to it, or we could say one extra discounting period since we're going backwards in time in this case. That's just the other side of that coin that we need to remove. We need to get rid of that, right? It's divided by 1 plus r, one extra time, if we move from an ordinary annuity to an annuity due, right? If we were to use the present value of an ordinary annuity formula to evaluate this annuity due timeline, then every single cash flow would have one extra discounting period attached to it or applied to it. And so this extra term on the end of the present value of an annuity due formula undoes that one extra discounting period, right? It's captured in this first part of the formula, and then this last part just undoes it. It undoes that one extra discounting period by compounding the entire value one time, right? And that undoes, right? If we have something in the numerator, it cancels out with what's in the denominator, and that's essentially what's happening right here. Okay, that sidetrack done. Let's actually apply this formula. We're going to look at both the formula and the financial calculator solution. So let's start with the formula. The present value of an annuity due is equal to the payment divided by the interest rate times the quantity, 1 minus 1 plus r to the n, and then that entire thing is multiplied by 1 plus r. All right, so let's plug in what we know. The present value is equal to the payment. In this case, our payment is $10 million. Our interest rate is 8%, expressed as a decimal as 0.08. We're going to multiply that by the quantity of 1 minus 1 over 1 plus r, so 1 plus 0.08 is 1.08, raised to the n. Now this is one place we need to be careful with an annuity due. The n is not going to match up with the tick mark where our last payment is. N is the total number of payments in the annuity. Well, although the last $10 million payment is underneath the 29 on our tick mark at the end of year 29, This is actually the beginning of year 30, and there are 30 total payments because we started counting at year 0. And we don't want to put 29 in as in because then we're telling the formula that there are only 29 payments to deal with, and there are actually 30. So in this case is going to be 30, just like it was with the present value of an ordinary annuity. And then to take out that extra discounting period that's applied to all of these cash flows, or each of the cash flows, all 30 of them, we're going to multiply this whole thing times our interest rate factor of 1 plus R. R again is 0.08, so 1 plus 0.08 is 1.08. And there we go, we've got everything in. Now it's just a matter of getting it through the calculator. All right, as I've mentioned in other examples, what I like to do with a long string of arithmetic like this is work it in stages and then store the values as I go. If your calculator is set up to follow algebraic rules of operations, you can enter it as it's written and it will work out just fine. It'll do everything in the order you expect it to, and you'll come up with the right answer, assuming that you key everything in exactly right. Particularly with the BA2+, we can't see the string of arithmetic that we've entered, so it's easy to type something in wrong, not realize it, and then hit equals at the end, and you get an answer back that's not right, and you have no idea why. So to address that issue, I like to break these into chunks, and then I'll store the values at each step, so that way if I mess something up, it's a little easier to go back and figure out where it's messed up, and I can generally get to the correct answer faster once I account for the mistakes that I'm likely to make in these problems. I'll get to the right answer faster by storing the values as I go. So I'm just going to work left to right on this one. 10 million divided by 0.08. Equals 125 million. And I'm going to store that guy on the 1 key so I can recall it later and I don't have to type the whole thing back in. That's, of course, a nice even number, so it's not like I'm increasing the precision by storing it. I just don't want to type all those keys again. Instead, I can hit recall 1 and pull the whole thing up. So that's why I'm going to store this one, and it's just a matter of habit for storing the values. All right, let's figure out what's inside the brackets now. And we can easily enough, again, type this whole thing in. I'm going to work it a little bit different. I'm going to do the 1.08 raised to the 30. I'm going to do that first. Then I'm going to put it under 1. I'll do 1 over that value, and then I will subtract that from 1, and I'm going to do that in this way. I'm going to start out by typing 1.08. I need to raise that to the 30, so I'm going to press y to the x, 30 equals, okay, so that 10.0627 is 1.08 raised to the 30. What I need to do now is invert it. I need to get 1 over 10.0627, and there is a shortcut on the BA2+ that will just put 1 over the value that's on the display, and that's this 1 over x key right here. If I press that, it inverts the value. Now this 0.0994 is equal to 1 over 1.08 to the 30. All right, so now I want to take this value and say 1 minus this value. So I could either store it here and then do 1 minus, recall that value, or another thing I can do is just hit the plus minus key to make this value negative and then add it to 1. All right, so that value inside the brackets is 0.9006. And I'm definitely going to store this guy because that is not a nice even number. Remember, the calculator has this worked out to 12 or 13 decimal places. And so when I store the value, it stores that full version that it has internally worked out, not just the 4 decimal approximation it's showing me. That's a pretty small number, and I'm multiplying it times a really big number. So if I were just to write down 0.9006 and then type that in later, type in 0.9006 times 125 million, I'm going to get a very different value than if I were to store the 13 decimal version of that number and then multiply it by 125,000 later. So this is one case where we definitely want to store the values because it can throw the answer off substantially. Okay, this, of course, 1.08 we don't need to do much about. We're going to multiply everything times that. All right, so now let's just multiply these guys together. We've got recall 1 is our 125 million times, recall 2 is our 0.9006, and then times 1.08 is the total present value of this payout option is $121,584,060 and roughly 10 cents. Okay, we came up with a value. What does this mean, the 121 million? What this means is if we were to look at this annuity payout option and we're to take each of these cash flows we expect to receive in the future and discount them back to today's dollars at 8%, which implicitly assumes that we're earning 8%. So as we receive that first $10 million payment, we're going to invest it and earn 8% on that investment. And so to find the present value of all these cash flows, we want to discount them back to today's dollars at an 8% interest rate. So the total present value of this annuity payout option, if we want to know what this is worth to us in today's dollars right now, it is $121,584,060.10. Right? And the reason that matters to us is we can now compare it directly with the lump sum payout option. If we were to take the lump sum payout, we'd receive $130 million today, so that's already expressed in today's dollars. If we were instead to select the annuity payout option, where we're receiving $10 million over the next 29 years, each year over the next 29 years, then in today's dollars, that's worth $121,584,060.10. Well, which one is higher, 130 million or 121 million? Well, $130 million is higher in present value terms, so we would want to take the lump sum payout option. So $130 million is greater than, that's a greater than symbol, believe it or not, is greater than 121 million, which means we should take the $130 million payout option. Because it is more valuable. We get that full 130 million up front. We can spend what we want to out of it, but we can also invest that full 130 million at 8% and go ahead and start letting it earn interest for us, which turns out to be more valuable to us than waiting to receive the cash flows over time. And when we're waiting to receive them, we can't invest them and start earning 8%. And it turns out in this case, although the absolute dollar amount is significantly less, 130 million is a lot less than 300 million, but because we get it sooner, we can invest it and start earning 8% on it immediately and let compound interest work for us. And so the payout option up front ends up being more valuable in this case. And that is extremely sensitive to the interest rate. If we wanted to play with this one and change the interest rate, the lower the interest rate goes, the more it's going to make sense to accept the longer term payout with a higher dollar value, because the present value is going to increase on that option when we're dividing by a smaller number. So this interest rate, for example, we're 3% instead of 8%, we're dividing by a much smaller number, and so the present value is going to grow, right? We're dividing a number in the numerator by a smaller number, which means the quotient is going to be larger, and the payout option over time is going to become more valuable. As the interest rate increases, though, if it were higher, say it were 12% instead of 8%, then the present value of the payout option is going to decrease and the upfront option becomes more attractive, which makes intuitive sense, right? With a higher interest rate, if you can earn a greater rate of return on your money, then you want it sooner so that you can then invest it and start earning that interest sooner, right? So that appeals to intuition. Okay, now let's look at the financial calculator setup. We'll look at the time value money keys for this one, because we're going to do something that we have not done up to this point. This guy's an annuity, so we can just use the regular N, I over Y, PV, PMT, and FV keys. And the entries are all what you would expect. N, again, is the total number of payments on this guy. So it is 30. There are 30 total payments of $10 million. The interest rate is the same 8%, which of course we put in as 8 because it's expecting a percentage. Present value is what we are looking for. Payment is the $10 million that we're going to receive 30 of. And then future value is going to be 0, not because the future value of this annuity is 0, but instead because what we're putting on these cash flow keys, the present value, payment, and future value, is actually what happens on the respective parts of the timeline. So payment is $10 million. We told the calculator we're going to get 30 of those. And so what we would put on the future value key is any additional lump sum that happened along with that last payment. Because we've already accounted for this payment, if there were some other payout at the end of this timeline, say there was an extra $10 million bonus at the end of this thing for delaying the payments, then we would have to enter that. In this case, there's not. There's just their regular annuity. Regular, not ordinary annuity, but regular, just a level $10 million payment over the next 30 years or 29 years, depending on how you're counting it. Okay, so it's just 0 for the future value key here because there's no extra payment at the end of the timeline. Now, here's where things get different. We need to tell the calculator that this is an annuity due instead of an ordinary annuity. So we need to put the calculator in begin mode. Okay? And the way we do that is, you see right above the payment key here, we have the letters BGN. That's what we're going to need to access to put it in begin mode. And it's written these grayish yellow letters. So we hit the second key to get there. We'll type second and BGN, which is right over the payment key. And you see it comes up with end. By default, the calculator is in end mode. It assumes payments are happening at the end of each period, which is what most annuities we encounter are. So that's what it is by default. We can switch that and tell it we're dealing with an annuity due by typing second and set, which is right above the enter key. And that works like a toggle switch that flips the calculator back and forth from end mode to begin mode. If I hit second and set, again, it flips it back to end mode. I want it in begin mode this time. So second, set. Once it says BGN here, we'll see the BGN in the top right corner on the calculator. And in fact, if I clear out of that, that's going to stay on the display. And that's kind of like a warning signal. The calculator saying, hey, I am in begin mode. I'm assuming you're about to tell me we're dealing with an annuity due, and that's not normal. Are you sure that's the right thing? So that's why this warning kind of stays on there, because it will stay in begin mode until you go in and take it out of begin mode. Okay, once it's in begin mode, we can enter these just like we would any other annuity. I'm going to start by clearing out the time value money keys by hitting second and clear TVM, and then I'm just going to work left to right. 30 is in. So I'll get 30 on the display, press the N key to store it. I over Y is 8, so I'll press 8 to get it on the display, and then press the I over Y key to store it. Present value is what I'm looking for, so I'm going to skip over that and go right to the payment of $10 million. So, and I'm taking the perspective of my pocket here, so that $10 million is going to be a cash inflow to me. I'm going to record it as a positive. You could take the perspective of whoever's paying out the lottery money, enter it as a negative, and it doesn't matter. You're going to come up with the same present value. It's just going to flip signs to say that the cash flow is moving in the opposite direction from that perspective. All right, but mine's going to be a 10 million positive number, so 10 million as a positive. Press the payment key to store it. Future value is 0. It should already be 0 because I cleared out the time value of money keys, but just to be sure, I'm going to go ahead and enter it anyway. Now I've got 4 of the 5 variables in there, so I can solve for the 5th. In this case, present value by hitting compute, present value, and we get the same dollar value we did with the formula, $121,584 and $584,060 and about 10 cents. That's probably not 10 cents. We're out of room on the display here, so that may be 9 cents, 8 cents. I forget. I haven't looked at the example in a little while, but it rounds to 10 cents, and that's close enough in this case. All right, so that is the present value of the payout option, which is the same number that we came up with using the formula. Now the sign is flipped on it, and the calculator is just telling us that that cash flow is in the opposite direction. In this case, It doesn't really know we're looking at a lottery payout option. So what that opposite sign is telling us is that if we were to invest $121,584,060.10 today, earn 8% interest on it, then we could make 30 withdrawals of $10 million starting today and then over the following 30 years. And we would exactly draw down that investment. The future value would be zero in that case, or the bank account balance would be zero in that case. So it's just letting us know that the relative direction of those cash flows are opposite. In this case, not a whole lot of meaning. In fact, if we, just so we can say we've done it, I'm going to flip the sign on that payment key, so it's now a negative, and they say compute present value, and we get the same numerical value for present value, just has the opposite sign. It's the negative sign in this case is not saying that it has a negative value. It's just saying the direction of the cash flow is different than between the present value and the payment key. Okay, one thing to make sure of, if you're working with an annuity due, as I said, your calculator is going to stay in begin mode until you take it out. So every time I finish working with an annuity due problem, I go ahead and put it back in end mode, just so I know that I've done it. So I'm going to hit second and BGN to get into that toggle switch to flip it back and forth from beginning to end. And I'll hit second and set to toggle it to end mode. We'll see the BGN came off the display. And then I can clear that out. I'm back in end mode and ready to start the next problem in the mode that I'm used to working out of.